Swayam Prabha. Digital India. Educated India.
Now, this is the topic today. We are going to discuss Spinel. Spinel are the ones which is, let's say, this nice looking gem looking thing, or gem basically magnesium aluminum oxide. It is beautiful in color. Okay, of course color comes from, you know where the color is coming from, those transition. Okay, now definition is Spinel is very simple. You can have either same metal or different metal. Okay, it could be, let's say, Fe3O4, CO3O4, or it could be MgAl2O4. Three metals should be there. Two of them should be the same, as you see. At least two of them has to be the same, will be the same, usually speaking again. Or one is different, MgAl2O4. Something like that. Now, AB2O4 is the general formula for spinel. The normal spinel are the one. There are two types of spinel. As I said, normal, there would be abnormal. Two spinel or inverse spinel. No, we don't say abnormal, inverse spinel. Normal spinel are the one where you have this electronic configuration. It is always going to be O4. Four oxides are there. That means -8. Each oxide -2, 4 of the oxide will be -8. Now -8 means you have almost one possibility, in realistic possibility, 3 plus 3 plus 2. Of course other possibilities are there, those are less likely. Never happens for spinel. So 3 plus 2. Since it is 3 plus, in the normal behavior or normal spinel cases, you would expect the octahedral geometry or octahedral geometry will be preferred by 3 plus and tetrahedral geometry will be preferred by 2 plus. Let us look at the, over here. Magnesium, aluminium. This is octahedral. You can see 1, 2, 3, 4, 5, 6. Each aluminium is octahedral. You look at magnesium, it is having 4 ligands. It's in a tetrahedral, I think most likely 1, 2, maybe 3 and 4. Magnesium is in tetrahedral geometry, aluminium is in octahedral geometry. Okay. Yes, so over here this is further showing you that 1, 2, 3, 4. So one of them, so it's a little bit complicated looking thing, but if you go by unit cell, if you break down the complex structure and look at the core of it, each of the metal ions, AB2O4, both the B will be in octahedral geometry. Okay? Sometimes it is just not clear by looking one glance at it. Okay? You have to just look it little bit carefully, you will be able to understand where it is. Okay? And these are usually the crystal structures, so there should not be any ambiguity, you just have to look it carefully. So both the octahedral will be in both the +3 oxidized metal will be in octahedral state, and the one which is 2 plus will be in tetrahedral geometry, and 4 oxides are there. If this is the case, this is normal spinel. If other way around, if one of these octahedral M3 plus has to be pushed out from this octahedral side to tetrahedral side, that will be called inverse spinel. So all it depends on whether one of these M3 plus will be in octahedral side or tetrahedral side. That's it. Of course, always there will be one metal 3 plus which is in octahedral side. This is common. the second metal 3 plus, whether it is exchanging with this other metal, that is what you need to see. Is it clear? Normal spinel, normal behavior. 3 plus should be octahedral, right? It's a privileged class. 3 plus, higher oxidation state, octahedral should be, right? It's a high charge, everything should be, ligand should be interacting more and so on. But that's like normal behavior. If it is other way around, octahedral site is coming out and tetrahedral is going into the octahedral one, or 2 plus is going into the octahedral one, this is when it is called inverse spinel, normal spinel. Now what is the criteria? Simply you have to see metal, this metal in 3 plus, whether it prefers octahedral or metal 2 plus, what it prefers. Let me show you. So M3 plus ion has, when M3 plus ion has a higher crystal field stabilization energy, okay, compared to M2 plus ion, then this is a normal spinel. Okay. If M2 plus ion has a higher CFSE, then it is inverse spinel. So you don't have to really look at the tetrahedral. You don't have to look at the tetrahedral. You take the metal ion, M3 plus, M2 plus, for a given metal ion, you find out M3 plus and M2 plus, their CFSE, separate CFSE. If M3 plus is more than normal, if M3 plus is less, having less CFSE compared to M2 plus, then it is inverse. Just read these two lines. So expectation is M3 plus in octahedral, and this is usually going to be high spin, should have high CFSE. Of course, opposite is true. M2 plus octahedral high spin should have low CFSE. CFSE calculation we have learned how to do. If this is done, normal. Opposite, inverse. Normal spinel, inverse spinel. Don't mix up with calculation of octahedral versus tetrahedral. Sometimes people end up doing that, they go into wrong direction. Okay? So you have to just calculate octahedral site stabilization energy. Like how much stabilization is there. So that's what it is written. M3 plus ion has a higher CFSE in an octahedral field compared to M2 plus ion in normal spinel, and so on. Do not calculate for the M3 plus in tetrahedral. Okay. Yeah. So this is where, I mean, yes, then how will you conclude? Right. So you have to figure out the stability of M3 plus versus M2 plus, right? This otherwise it will get confused. What will you be comparing with, right? CFSE for tetrahedral is usually low, 4/9 of delta O. What to calculate? Okay. So let me give you an example. It will be clearer. Yeah. More negatives. See, in terms of energy in chemistry, physics, everywhere, energy means the one which is having low CFS or low anything, low repulsion is stable, low energy, I mean, it's stable. Okay, anything low would be stabilized. It's like, as I was trying to say, it's like home feeling. You want to feel home. Everybody wants to belong somewhere, and that's where they want to go, right? So always low. Okay, stability should be maximum. Yeah. No, that is the splitting delta. So that is the splitting we are comparing. When we are not changing anything, ligand keeping constant, metal oxidation state varying, metal with a higher oxidation state will have higher splitting. Okay, that is somewhat true here, but I mean we are not saying the extent to which. We are trying to tell here is M3 plus M2 plus, yes, you are partially right, M3 plus M2 plus, you just calculate the CFSE. Okay, let me give you this example, hopefully things will be clear. Okay, Mn3O4, okay, Mn3O4, of course here oxygen usually always, I mean not always, again there will be one example which is other way. Usually oxides for these cases are going to be the weak field ligand. Okay, it is a weak field ligand. Now, unless the metal is very high, very high oxidation state or so, oxide will be the weak field ligand. Okay, you don't have to worry about the oxide too much, except in one question which will come. Manganese 2 plus D5, since it is weak field ligand, it is a high spin. That's what I was saying, high spin. Now, high spin is 0 CFSE. Manganese 3 plus D4 is T2G3 Eg1. So, you are going to get net minus 0.6 delta 0. That is what you have calculated, right? Should be okay. Minus 12 minus 6. So, sorry, plus 6. Minus 12 plus 6 is minus 6 dq. Okay. Now, this is the normal spinel. How about Fe3O4? Can you calculate Fe3O4? Whoever is trying to calculate, give yourself 1 minute. Fe3O4, Fe3 plus and Fe2 plus. Okay. Okay, whoever got it, hold on for a minute. Inverse spinel, yes, that's the correct answer. Just in a moment I am looking for something. So I hope you have got this, right? Fe2 plus D6, T2G4, Eg2, high spin, 3 and 2 cancels out, 3 over here and 2 over here cancels out, so minus 4. It's easy, right? Over here 3 and 2, 0 CFSE, right? Now, Fe3, as you can see, is having less CFSE compared to Fe2. So that's it. So inverse spinel. Only request is do not complicate too much. You think, but for calculation do this. Because if you end up calculating tetrahedral, Fe3 plus case tetrahedral, Fe2 plus case tetrahedral, it's going nowhere. Okay, it's a simple thing. Higher oxidation state should try to stay in the octahedral side. The moment higher oxidation state becomes less favorable compared to the lower oxidation state, switch of the power happens. It's just the BJP and Congress. You have to pick up one of them in the center, not the local, okay, or Democratic or Republican. You do not have any choice. Okay, now, so this is the special case of D8 octahedral, right? So what is the special case? We are alluding before that these Dg2 orbital are the one getting repelled by 2 electrons. This is a D8 electronic configuration, as you can see, T2G6 Eg2, and this is the one repelled by 4 ligands. Okay, that is unfair. That is where what happens is Z orbital, okay, try to stabilize, to minimize the energy, to gain more energy. So you start with an octahedral situation, but you see D8, you go blank. D8 octahedral will tend to form square planar geometry. Okay? Because the Z, you will see square planar complex is formed because Z will get destabilized, stabilized. Z is getting stabilized, as you can see, Z orbital will get destabilized. This is an unfavorable situation. This is a situation which cannot be tolerated. This is 2 ligands repelling, 4 ligands repelling, right? This is the unique situation, 1 unique situation, same electron repelled by 1 electron, repelled by 2, 1 electron repelled by 4. In order to bring some sort of calmness to the system, Z orbital will stabilize. If you want to stabilize x2, y2 orbital, then the problem becomes stabilization means repulsion is less. That's the stabilization. Repulsion less is the stabilization. If you want to stabilize dx2, y2 orbital, then you have to elongate 4 of the ligands. Stabilization means reducing the repulsion. If you are stabilizing Z square, then you just need to take out those axial ligands. It was here, 2 axial ligands over here, you pull it out. So Z will be stabilized, dz square will be stabilized. Of course, further it will be stabilized. Any Z component there will get stabilized. So dxz will be stabilized, dyz will be stabilized. This is the scenario where square planar complex goes. D8 octahedral usually will be, if it is possible, always it will go to the square planar situation. That is also true. D8 tetrahedral or D8 4 ligands are not tetrahedral. D8 configuration 4 ligands are going to be square planar. Okay? This is where you see iron, cobalt, nickel. Nickel is nickel 2 plus D8 is square planar. All right? Now, this is one scenario. Other scenario is that EG orbital is unsymmetrically filled. See, you can see that majority of the syllabus is biased towards octahedral. Okay. Tetrahedral not too much, but that's because octahedral is favored, octahedral is historically more important, and that's what most of the study has been done, and it's a common geometry, more common geometry, I would say. Now, this is the Ian-Taylor distortion. Of course, some people pronounce that differently. In British, in England, you will go pronounce differently. US, it will pronounce differently. Ian-Taylor, some people tell Jan-Taylor, whatever it is, it's the same thing, JT distortion. So what we see, if this one is unsymmetrically filled, what are the situation when it is EG3 or EG1? That's the only two possibilities. EG2 will be symmetrically filled, EG4 will be symmetrically filled, EG1 or EG3. If it is filled, then again you are having some sort of a problem. What is the problem? That is what we are coming to. Let me go to the picture. Okay, this is what is Ian-Taylor distortion. If, of course, T2G is completely filled, okay, completely filled or symmetrically filled. Either T2G is T2G3 EG1 or T2G6 EG3, all these configurations. So what are the configuration? T2G3 EG1, T2G6 EG1, T2G6 EG3. So wherever unsymmetrical situations are possible, of course, T2G3 EG3 is not possible, right? T2G3 EG3 is not possible because it would be T2G4, T2G3 EG4 is not possible. So this sort of thing you should be able to recognize very quickly. T2G3 EG4 actually should be T2G4 Eg2, right? Why means it's a stabilization. You look at. Very good question. Right. So T2G3 Eg, sorry, Eg, this is, did I say 3? Everything I said is correct. 3 plus 3, 6, 4 plus 2. Okay, 6. Now T2G3 Eg2, this is the T2G3 Eg2, high spin if you are even saying. Now how it can be going over there? Because it is giving more energy or destabilizing the system. This 6th electron should come here. See, always filling rules anywhere. I mean, you read the Hund's principle, you read whatever other principle, system has to be stabilized. When two scenarios are there, system goes for stabilization. But when high spin, low spin situation is there, because high spin is accessible, it goes for high spin, or it can go to low spin. Here, after filling out 1, 2, 3, if it is high spin, 4, 5, 6th electron will come back from here. It's home, right? It's stable. So T2G3 Eg3 is not a valid configuration. It is T2G4 Eg2. It is invalid. I mean, literally, it is possible for an excited state. If you excite T2G4 Eg2, then it can come to T2G3 Eg3. This is usually all we are talking about is ground state electronic configuration. Okay? Any confusion on that? No, hopefully not. Now, Jahn-Taylor distortion, T2G either fully filled or half filled, T2G6 or T2G3, here it has to be unsymmetrically filled. Means Eg2 and 4 is out of question, Eg1 or Eg3. Two orbitals are there. Okay. What can happen? Two scenarios are there. Either Dg2 can be stabilized or Dx2Y2 can be stabilized. Now stabilization, again stabilization means what? Stabilization means repulsion is less. Okay. Stabilization means less repulsion. Less repulsion when it can happen? When ligand is not coming. If Z square is stabilizing, that means along that direction ligands are far. So this will be too long, that will be so the left hand scenario, this is a base for octahedral scenario we are drawing. This is the equatorial plane, axial was here. Now this is, let's say, normal scenario. If I want to say that dz square orbital is stabilized, that means this ligand is not, this is the dz square orbital direction, right? So that means ligand is not coming close to this dz square orbital. This is where the dz square orbital is, right? So it is not coming close, that means it is going far. And that is how dz square can be stabilized. That means two of the ligands should be at a longer distance and 4 of them at a shorter distance or relatively shorter distance. The opposite is here. When relatively speaking dx2y2 is getting stabilized, that means these are going out. Stabilized means repulsion is less, ligands in the second scenario, ligands will be further away. And Z was over here. So Z in, this is called Z in. Z direction getting in. This is called Z out. Okay? It's a very, very simple thing. If you just try to understand very simply Do not complicate things. It is that very simple. Now as you can see, Z out, this is the Z out. If you keep on moving more and more, Z out becomes your square planar, right? So here, previous case, what we were discussing. If Z becomes stabilized more and so that it is, you are taking too far from the metal center, octahedral is no longer octahedral, it is becoming square planar. Okay, so Z in and Z out. Yeah. Sorry? No, these are having same energy, right? No, these are degenerate. You cannot dictate the term, you cannot tell who is where you want. It's just, this is just for nomenclature's sake I have written, just to, just to tell you or just to write you something I have written. Which one is dz2 or which one is dx2 you don't know. It is same energy, right? Degenerate means same energy. 5d orbitals before crystal field theory, we used to think that it's same energy. We don't discriminate, right? So this is just a representation sake. Not all the cases, but when it is unsymmetrically filled, then it is becoming a problem. See, 4 scenarios are there. Eg orbital. Why Eg orbital is getting perturbed, why T2G not? Because those are the one, you can see these are the outside. If you see the splitting wise, those are the one facing the maximum of the ligand repulsion, right? In Eg, 4 configurations are there. Eg1, Eg2, Eg3, Eg4. Eg2 scenario we have already discussed. Eg2 scenario is the one where we are getting, most often we are getting that D8, T2G6, Eg2. That is a D8 electronic configuration, it tends to go for a square planar one. Fine? You remained with Eg1 or Eg3. Eg1 and Eg3 scenario we are trying to discuss here. So when it is symmetrically or full filled, then usually we don't get bothered. It's, other way, one way or the other, it is just the same. I mean, it's completely full. So nothing to really compare with. But in this scenario, when you have unsymmetrical filling, then you have the chance of splitting. See, similar split, the extent of splitting you can see is not the same here again. Of course, usually speaking, these are the one, Eg are the one which are going to face the ligand directly and thereby splitting starts over there. And then of course sometime it also get affected, T2G gets affected. That's why we were showing, initially we didn't split it. Initially when we were discussing T2G6 Eg2, we were showing that dz2 is getting stabilized. When it is getting further stabilized, and this, then it is going to get split further. Okay? So look at the slide. Almost in every book it has been written really well. If you have any confusion, please come back, okay, or discuss with your friends. So Z in and Z out. This is Z out. Z out means Z, you are pulling out, stabilization happening. Okay. Now this is a slide which is mostly left for you to digest a little bit. Square planar geometry. So if you want to memorize, sometimes things can be problematic. We want to read you mainly, let's say, octahedral, 3, 2. Octahedral, where is tetrahedral? Tetrahedral is not given here anyway. The geometry and thereby they are splitting, how they are going to split. This is not all of them is part of the syllabus again. This is just an overview giving an idea how ligands are coming, how d orbitals are getting perturbed, which direction d orbitals are located, and then from which direction ligands are coming. Of course, that is what going to determine what is their geometry. If it is a square planar, where it is coming, you know. If it is a trigonal bipyramidal or TBP, 3 of them in the equatorial plane, triangle, 1 from the top, 1 from the below. So which are the orbitals going to get affected and to what extent, and so on. So these are, these are in the book, or may not necessarily you have to read it. You are, but you are supposed to read octahedral, tetrahedral, square planar. I think for fun you can look at that, try to justify a little bit. Okay? So that's it for this chapter.